we'll talk about what's called point mass versus an extended object. Let me give you an example of that first. How many of you, show of hands, how many of you could lift, could lift a 5-pound dumbbell? 5 pounds. You should all raise your hands. I'm pretty sure everyone in the room can lift a 5-pound dumbbell. Okay? But when you get to certain weights, like 30, 40 pounds, it gets a little harder. But honestly, show of hands, who thinks they can lift like a 30 or 40-pound dumbbell? Be honest. Okay. Now, out of those hands that are up, can you lift the couch by yourself? Can you lift the couch by yourself? Any of you? Honestly?
Again, it depends.
It'd be really tough, right? It depends. What does it depend on? No, that's a great answer, and that's the answer I was looking for. What does it depend on?
First of all, the mass of the couch, obviously.
Let's assume it's 40 pounds weight. Same as
also, the width of the couch.
Yes. Why? Why does that matter? Good. Why does it matter, man? Help me.
It'd be like impossible to rip it and pick it up. Like if someone like picked it up for you
And put it like in your arms, maybe you could, right?
arms like on your back or something, you could hold it.
Sure. But with a 40-pound weight, you could do it. They're both 40 pounds. So what's the physical difference?
Area or like surface.
Yeah, area or distribution, let's say. The mass is distributed over a longer part. So when you try to, you can actually try this. It's not, take something that's very light, but put it on a long, long, long rod, imagine like 3, what are they called? A dowel rod from a broom. What is that called? The handle, whatever. They take a broom and cut off the end of the broom. If you attach like 3 of these together, and you only put like 5 pounds on each side and try to walk with it, it would be very difficult. You'd have a lot of trouble actually balancing it. Now, if the weight is at the very ends, actually tightrope workers what a tightrope, ever seen a tightrope walker walk? They actually use poles to help them keep their balance, but they're not extremely heavy. So if you had something where the mass is distributed like a couch, it's very difficult to lift those 40 pounds because it's going to wobble, right? You're going to walk oddly because of the fact that there's torque. There's a moment on each side pulling you down both directions. With a 40-pound weight, that doesn't happen. It's a concentrated, what we call, in this case, point mass. We've studied everything this year as a point mass. We've said all right, an object is being pushed. What do we usually do? We draw a free body diagram. It's just a little box or a dot. But we don't look at the dimensions of the object usually. It never really has an effect. Yeah, you push it with a certain force. Let's find the acceleration. The dimensions of the object never came into play. Now we have to be concerned with the fact that you could have a point mass, or you could also have an extended object with a distributed mass. A distributed mass is the easiest way to say it. So that's what we're going to look at with torque today. We're going to talk about torque acting on an object, and then rotational equilibrium. What was equilibrium in general? What does the term equilibrium mean to you? Equilibrium. Not moving. That works. Not moving. Specifically, force equilibrium. Force equilibrium, what is that?
All the forces are equal to each other.
Yeah, the forces are equal or balanced, right? There's a balance. So if you think about 2 people pushing against each other, if they're unable to have any motion, so like this would mean that this arm is stronger than this one. But right now, they're together. If you had a tug of war and then nobody was moving, it would be an equilibrium. But the minute there's no longer equilibrium, it causes motion. So in this case, yesterday, your goal was to find equilibrium. That's what you did yesterday. When that beam was at a balance and it was stationary and it was not rotating due to a unlevel mass balance, it was in a state of equilibrium. But not equilibrium like we've seen with forces, but in this case, what we call rotational equilibrium. Okay? So let's start with the word torque. We haven't really defined it, but we've really utilized it a lot. So the simple definition is a force applied at a given distance from a fixed point. So look at the diagram. If it's not clear what we're talking about, here's the force. This force is applied at a given distance, the distance measured by r from here to here, and it's usually from a fixed point, which has happened to be here. See that? It looks like there's like a nail, like it nailed in. Okay, so imagine you took like a beam, you nailed one end in, well that beam would be able to rotate about that nail. If I nail both sides in, can I rotate it now? No, that should be common sense, but it has to do with what's called degrees of freedom. So if you only nail one nail in here, this has the freedom to spin, to rotate. The minute you put a second nail in over here, it's like when you hang up a picture. Did I use that example yesterday with you guys or no? You hang a picture on the wall. If you put a nail in the middle, it usually works all right. It's not bad, but it could kind of sway a little bit, or if somebody knocks into it, it sways for sure. So what do you sometimes do? You put a nail in each corner, and you hang it on the both corners, and it's nice and level there. Okay, but if it's in the middle and you walk by, and I just walk by that picture, right, and I hit the picture frame and I hit it, it's going to rotate if there's only one nail in the middle. Because there's tape here and here, this is not going to rotate at all when you hit the actual object. So in these problems, usually there's some sort of a fixed point. And the fixed point means it cannot change its position. So everything else can move, it can rotate, but this will not change its location. Which way would this force cause rotation? Clockwise or counterclockwise? If you don't know, just show me with your hand too. Mike, what do you got? What do you got? I didn't hear you.
Clockwise.
Clockwise. So think about this force being applied. If I had, I mean, you could do it anything, really. Use the hammer as an example again. Okay, here's the hammer right here. If I were to, let's do it this way. Let's make believe this is a nail on the wall. Okay, here's the hammer right here. And I apply force down. It's rotating this way. Do we all see this? It's very important that you get what I'm saying right now, because it's going to involve all the math this chapter, or this section, is going to be based on rotation. So if I'm on this side of the fulcrum and I pull down, this entire body could rotate like this, right? That's called clockwise, because it's the same direction the clock moves. And then if I were to say, go like this and push up, it's going to cause it to rotate. What do we call this? Counter, or anti-clockwise. It's called counterclockwise, but some books are online, you'll see the word anti-clockwise. Same thing, okay? So this force would cause a clockwise rotation in this case. If the force was applied from below the beam, it would cause a counterclockwise rotation. R is the distance between the actual rotating point, or point of rotation, and the force applied. We call R the lever arm. Okay, and we'll talk more about the lever arm in a minute, how the lever arm can change based on the angle. F is the force applied. The angle is the angle that is made up between the lever arm and the force. If you were to extend your lever arm and force, okay, if you were to extend it this way and see, we'll see that this could also be considered the angle over here. Again, the lever arm and the force, what angle is made up? We call that theta. I could also use theta on the other side. What do they differ by? How do I know the difference, or what's the relationship between theta 1 and theta 2? What's the relationship that exists between them? 180 degrees, good. They are, what's the word for that, so we know? Supplementary. Okay, so those angles are supplementary. And in this formula, we're going to be multiplying our values R and F by the sine of that angle. Quickly, take a calculator out. Make sure your calculator is in degree mode before we do the next thing we're going to do. So hit mode, and make sure degree is highlighted. Pick an angle. Any angle between 0 and 90 you pick. Don't make it 90, okay, or 0. Anything between 0 and 90 exclusively. So once you pick your own, each of you pick your own angle. Pick your own angle, do the sine of that angle. Get an answer, it's on your calculator. It doesn't matter what it is, just look at the answer real quick. Now, do the sine of the supplement. So if you did 50, your supplement is 130. If you did, 70, your supplement is 110. So figure out what 180 minus the angle you chose was and do the sine of that. So if you did the sine of 50, do the sine of 130. If you did the sine of 60, do the sine of 120, whatever the supplement is. What do you got, Tiana? It's the same answer. It's the same answer. So in this case, and you're going to learn about this in math this year, actually. You're going to learn about what's called the unit circle in your third and fourth quarter. Now, I think actually it's more toward the fourth quarter, but you're going to see why that's the case. I'm not going to go into detail about why it is yet, because there's a lot more theory behind why it is. But what I want you guys to recognize here is that the angle, theta 1 and theta 2, although they look different and their values are different, if I take the sine of either of those values, I get the same number. Okay? I get the same number. Now, traditionally, torque is applied at a right angle. For example, if I did this again, I'm not going to do it again. But if I wanted to take this nail out again, when the nail was on the table right here, I hook the hammer underneath it, and notice the way I pull? I pulled straight back. Look at the hammer and look at my arm. What angle do they make up? My arm and the hammer, what angle is that? 90 degrees. I wouldn't do this. It doesn't make sense to go like this. I mean, that angle is like 20 degrees, 30, 40, or 45, 50, 60, 70, 80, 90. And then up here would make sense either, right? Remember yesterday? No, you didn't even do that yesterday. In the other class, I talked about this yesterday. If I applied a force at an angle of 0 degrees, it would look like that. Am I going to get the hammer to rotate by pushing down on it? No. But if I start changing that angle here a little bit, it rotates. If I change it here, it rotates. As soon as it's either anything between 0 and 180, it's going to cause rotation. What's going to give you the best rotation is 90 degrees. Type in sine of 90 on your calculator. There you go. 1. Any other sine value is less than 1. So if you want to get maximum torque, the best angle is 90 degrees. If you want to get maximum torque, the best angle is 90 degrees. The worst angle, 0 degrees. Type in sine of 0 on your calculator. There you go. 0. That's the example that I just told you. Imagine this is the setup right here. And I want to make this object rotate. Right? So I want to take this object that's on the board here, and I want it to rotate. So, okay, you know what? I come up next to it and I push like this. I'm pushing. I'm pushing. Is it going to rotate by pushing this way? Of course not. The rotating axis is here. All I'm doing is compressing the member. I'm trying to squeeze it in a sense. I'm trying to make it, imagine I don't know, just get over here the other day. What I'm doing, what I'm saying is like this. Imagine this is the object right here. Okay, it's fixed on this end. As soon as I push down, it rotates. Push up, it rotates. Push at an angle, it rotates. Push at an angle down, it still rotates, right? You all see how it's going to rotate if I'm pushing up or down on it at an angle? But now I'm going to push this way. Is it going to rotate? No, I'm literally compressing it. That's what I'm doing. I'm bending it, compressing it. But if I push like that, it's never going to rotate. Well, if the force acts to this way, let me draw this on the diagram so you can see it now. If the force happened to be this way, well, that force being applied from the right is the exact same, or it's collinear. What does the word collinear mean again? On the same line. This is your geometry class. So the twig, or the dowel rod is the line. The force is applied this way. The lever arm is this way. What's the angle between these? What's the angle between this and this? How much of an angle is that? 180. Type in sine 180. No? What is it? Sine 180? 0. It's the same as doing sine of 0. So if I apply a force from the right that is parallel to this axis R, it's automatically not going to give me any torque. It's common sense because you physically can see that if I want this to rotate and I just push on it, it's not going to rotate. If I push down on it, it will rotate down. It will rotate up easily. But if I push like this, where the axis itself and the force itself are parallel or collinear, it will not produce any torque because the angle would be either 180 or 0. You could either consider one. Either one works there. So let's jot down a general conclusion about our angle. Actually, let's go to the next slide to see our conclusion about the angle. So in the next slide, we talk about what's called the lever arm, which is really that R value. Okay, but what you can notice is that based on the angle, the lever arm actually changes in length. The lever arm is technically, this is tough to see, but the lever arm is technically always going to be perpendicular to the force itself. So take a look at this diagram and follow in this direction. This is an annoying diagram. It's a great diagram, but the way they orient it is wrong, actually. So this is scenario 1, 2, 3, 4. Okay, so look at it in that order, please. So in scenario 1, I've got my torque wrench. My angle between the actual wrench and my force is what degree? 90 degrees. And therefore, this produces the most torque. Because you guys saw a minute ago that the sine of 90 is 1. Now, if I type in the sine of any other angle, it's going to be a decimal. The sine of any angle except for 90 is going to be a decimal. And some are 0 and stuff, but it's going to be between 0 and 1. So 90 will produce the most torque because sine of 90 is the greatest possible value for the sine function. Now, if I look at this next part here, what I'll notice in this part is that if I were to look at my force, okay? If I were to look at my force, I could think of drawing my force, another vector that is parallel to the force, and connecting them. And this is considered like my quote-unquote, my new lever arm. Because this angle has changed, this is now the lever arm. And then the lever arm is here. And then the lever arm is here. What's happening to the lever arm as I change each of these diagrams? Physically, what's happening to its length? Yeah, it's increasing or decreasing. It's getting smaller. So the actual leverage you have changes based on your angle. So you could think of the lever arm as r sine theta, and that's in the formula. It was r f sine theta. So that r sine theta could be thought of as the lever arm together. So what I want you to recognize, though, is this. And this is the conclusion I want you to draw from this. If theta changes, as theta increases, tau increases when theta ranges from 0 to 90. Okay, I'm writing my finger to charge my pen, sorry. So theta increases, tau. Tau, this symbol here, I should have mentioned that word. Tau, have you seen this before? Maybe, no? Never? You never seen tau? Okay. It's like a Greek symbol for the letter T. Instead of using a capital T, you use the symbol tau for torque. Okay? Think of tau, T is torque. So tau stands for torque. As, not twerk, but torque. Okay? As theta goes up, because they sound similar. It always sounds like saying twerk. As theta goes up, tau continues to go up. But what happens after 90 is this. After 90, from 90 to 180, it starts to then decrease. So if I have an angle, or if I have an object here and I'm rotating, I'm pushing out at 90 degrees. If I lower my angle, I'm getting less torque. If I lower it even further, I get no torque. Now I'm pulling up. Technically, if it's 0 degrees, I'm pulling up. Now, if this is 90, now it becomes 110, 120, 130, 140, until I get to 180, and now I'm getting no torque again. So what happens is that tau increases as theta gets bigger, but only up until 90 degrees. After 90 degrees, tau, as theta increases, tau decreases after 90 degrees. Okay, so from 0 to 90, if the angle gets bigger, you get more torque. But then at 90, you reach maximum torque. After 90 degrees, what happens? The torque starts to decrease because you're getting less and less and less leverage until you get to 180. And remember that the sine of 0 and the sine of 180 are both 0. When you type those in your calculator, you get 0 for both of these, which is why you get no torque when the angle is either 0 or 180. So again, the lever arm we want to think about as the perpendicular distance from this rotating axis right here to the force. That's that distance right there. Okay, now, if we have a problem, obviously, where in this case, we don't really want to use this length here. Technically, we're using this length right here. Or this length right here. Or think about it as this length right here. Okay, between the rotating axis and the force, what's a perpendicular line? That's a perpendicular line. So that's considered the lever arm. So what's happening as your angle gets bigger is your lever arm is getting smaller, or you're getting less and less and less torque out of it. Okay, if you get an angle here, it goes from 90 to 80 or whatever that is, 70 to maybe like 45 to like 20 degrees in this last diagram. But the key is that after 90 degrees, then opposite happens. You get more torque up to 90, less torque after 90. Let's do a little bit of math with an example, and I think it'll help maybe just explain this a little bit better too. So this first example is a little bit easy. The reason it's a little bit easy, what are your angles involved here? The force is applied straight down. What's the angle going to be? 90 degrees. Look at the lever arm. Here's the length of the wrench. The force is applied straight down. What angle does that make? 90 degrees. If you're not given an angle, it's probably 90. It would say in the diagram what the angle is, though, if you had to use it. Is that clear? So in problems where an angle isn't given, there's a good chance the angle you're going to use is 90 degrees. In this course, at least, if you take AP Physics next year, you'll see that it could change a little bit, and you sometimes have to use a little bit more trig to figure out what that angle is first. So in this case, the question is posed, there are two people pulling on this object. Which of them produces more torque? The first one or the second one? So we have to think about yesterday, what was the actual formula for torque? So today's formula, or what was the idea yesterday that we came up with for torque? Yeah, it was how far away you were, and it was how much was hanging, right? So in this case, because we're using our torque formula, we could use, remember yesterday we said we were looking at like really the distance it's applied at and how much mass. Well, today we're going to say this is the same thing as R times F. R is the distance, F is the force. Yesterday, the hook number was the distance, and the mass was like the force. The mass of the object hanging applied weight down, which is a force. So these are analogous. What we came up with yesterday is exactly the formula for torque, really, except with different variables. So instead of mass, we use force. And then D is the same thing as R, really. Okay, it's literally the same thing. It's the lever arm. Now, obviously, we have to multiply by sine theta, but in both of these problems, it's sine of 90, and the sine of 90 is 1. So that has no effect on the answer. So a force of 20 newtons, 1 meter out, or a force of 10 newtons, 2 meters out. Which supplies more torque on the actual bolt? Which of these two? It's the same. Okay? And this is kind of what you saw yesterday. Think about the examples yesterday. Hook 1 with a mass of 100 was the same thing as hook 2 with a mass of 50. Think back to yesterday's numbers. Hook 1, the distance of 1 whatever, with a mass of 100 was the same thing as hook 2 on the other side with a mass of 50. Because you did 2 times 50 over here and 1 times 100 over here, and in the end they'll balance. So in this case, both of these scenarios generate 20 Newton meters of torque. So this is scenario 1, and this is scenario 2. Those are the two scenarios represented in this diagram. They are both causing this object to rotate which way? Which way would the bolt rotate based on these forces? Very good, clockwise. And if you don't know that, ready? Here's how you do it. Here's the rotating axis. Go to the force and move your pen along the direction of the force. Okay, so watch what I'm going to do. I'll take the pointer and move it down because the force is acting down. Well, if I pull down and I want to circumnavigate, I guess? I don't know. No, it's around the Earth. If I want to orbit, whatever. If I want to rotate around this central point right here, the only way to go down and around is to continue this direction. Okay, a lot of it, honestly, is common sense. If you think about it physically, pulling down this would cause it to move down and would cause this object to rotate like this over and over and over again. How many of you have heard the phrase lefty-loosey, righty-tighty? Raise your hand. That is the worst phrase ever. It's great because you understand what it means, right? But why is it the worst phrase ever? Because yeah, it's righty, but it should really be clockwise is tight, counterclockwise is loose. What's right and left, really, when you think about something rotating? For example, a Ferris wheel, okay? It's rotating. Would you say it's rotating left or right if I did this? Left or right?
From our perspective, left.
From your perspective, left? Okay, so at the bottom, which way is it rotating now?
Right.
At the top, which way is it rotating now?
Left.
So both answers are correct. You see what I'm saying?
Yeah.
When an object rotates, it doesn't rotate right or left. It rotates clockwise or counterclockwise. Is that clear? With a screwdriver, yeah, it's great. Righty-tighty, lefty-loosey. With a sink, when you open a faucet, usually right tightens it, left loosens it, because there's a little valve on a little thread that spins. That's all it is. But you need to recognize that when something is rotating, it's not moving left or right. The bottom could be moving left while the top moves right. And that's how a Ferris wheel is, right? This is what's happening. It's literally that. The top is moving down while the bottom moves up. That's how a Ferris wheel works. Because if you're sitting at the top, you're moving to the right. But if you're sitting at the bottom, you're technically moving to the left. Is that clear what I'm saying? So let's adopt a nomenclature in this class. And here's how it is. This is going to be our sign setup. So in physics this year, we talked about how up is positive and down is negative. How right is positive and left is negative. We need to adopt a system of signs for this also. If you want to look it up, maybe somebody will look up why this is. I'm not sure the reasoning actually. But the adoption that we've always taken in all of science and engineering and math is that clockwise is negative actually, and counterclockwise is positive. It's a bit counterintuitive, to be honest. Because when I was young, I remember my teacher telling me, I was like, shouldn't clockwise be positive? It makes sense. That's like you're adding time. Positive, positive, positive. Whereas the other way, you'd be taking away time. This is just the adoption that scientists have used for hundreds of years. That counterclockwise is actually considered positive. Okay, so the bottom one is counterclockwise. That's positive. Whereas clockwise is negative. It doesn't actually matter. If I call up negative, then what's down? If I call left positive instead of negative, the other way is negative instead of positive. It doesn't actually matter as long as you are consistent in the problem. Okay, and you'll see that in about a minute or two when we get to an example with that. So torque, what matters? The force applied, how far it is from the fulcrum or the rotating point, and the angle that it's applied at. Those three things. That's why it's R, F, sine, theta. I can't implore you enough that you need to understand why the formulas make sense. Torque equals R, F, sine, theta. R is the distance away. As you move further from the rotating axis, you get more torque, like I showed you with the hammer. F, how much force you apply. That's common sense. You push harder, you get more torque. Theta, not as obvious, really, right? We talked about that a little while ago. But recognizing that R and F are directly related to torque. Okay? R and F are directly related to torque. So in this case, since this caused the object to rotate clockwise, right? Let's go back to this problem. This arm pulling would cause a clockwise rotation. Technically speaking, these are both negatives. That's how we adopt it. It's not about the force being down, you put a negative here. Forget the direction the force is applied. Think about the way that it would rotate based on that force alone. Okay, so both of these cases, the answer was negative 20 Newton meters. That's something else I should really emphasize real quick. When you guys calculated work, what was the energy for work done? Joules. Good memory. You got to know these units, right? That was the unit for work done. Well, you know what? That's kind of misleading because look, at the bottom, let's write down what work is. Isn't this work really right here? Isn't that work at the very bottom right there? FD cosine theta? It's actually very similar to torque. F is in torque. D is what, really? D is distance. R is a length in meters. They're both meters. And then cosine theta, sine theta, not much of a difference. So the units of work were technically Newton times meter. And that became joules, right? That's where we came up with joules. For torque, though, you do not use joules, which is, again, counterintuitive. Okay, and I try to point out these things that are counterintuitive because it's common nature for you to think that, oh, you know what? If a Newton meter was a joule earlier in the year, then Newton times meter could be replaced with joules again. And it makes sense to think that. It really does. But it's not actually written that way. That's how we differentiate between torque and work. The units of torque are Newton meters. The units of work are joules, although they're both really the same units. We write torque as Newton meters and work as joules. If you have a torque wrench, usually it has a rating on it of how many pound-feet it can produce. Pound-feet, Newton meter. Pound is a force, feet is a distance. Well, Newton is a force, meters is a distance. So when you see a torque wrench at the store and it has a value on it, it tells you, based on this torque wrench, you can produce this much pound-feet of torque. Pound-feet is a Newton meter. Not the same value physically, but the same entity. It's a force times a distance. Okay, or a force times a length. So let's look at this example. Find the net torque acting on this object. The object has no mass. That's really important, by the way. That's massless. If the object had mass, it'd be a little bit different. And if you're intrigued, seriously, take AP Physics next year. That's something that you will cover for sure. When the object has a mass, how does that affect the problem? And we're going to simplify things for a little reason here. For a little bit here for a specific reason. So the question is, will it end up moving? And if so, in what direction? Predictions. Don't do any math. Predictions. Will it move? How many hands for yes? Will it move? by will it move, I mean will it rotate, I should say, sorry. Will it rotate is the question. If it were to rotate, how do you know which is going to be, is it going to rotate this way? Or is it going to rotate this way? Why would you say this way, just hypothetically? This is a total guess, so you can be right or wrong, don't worry. Why would you say this way? Why would you say clockwise?
It's pushing down.
Because this is pushing down over here, right? But what is this side doing? So what are they doing to each other, kind of? They're kind of like balancing or forcing against each other. One torque pulls this way, one torque pulls it this way. So in reality, this member would probably it might bend a little bit, really. Now, I see a lot of hands. Can you give me some feedback? What's going on here?
Okay, I would say that it would probably lean more downward on the left side because the left side has more force and is straighter, is moving at a 90-degree angle downward.
And what else? One more thing.
It is also further to the left from the.
Yeah, look, there are 3 reasons that, even though I said take a guess, you couldn't really come up with the answer, that this one is stronger than this one. The value of the force is greater. You see that? The distance, r, from the fulcrum is greater. 4 is greater than 3. And then remember 90 degrees, wasn't that the most torque from 90? So this is going to give us less torque. So I know already that this object will rotate, okay? It will rotate in this fashion. And we call that counterclockwise. Now, I don't know for certain what the value is, so I still have to actually figure out what the value is. It says, will it end up moving on, actually in this case, is will it end up moving, and if so, which direction? But the first part says, find the net torque. What does net mean again? Net means? Total. Yeah, total. Sum everything together. So let's find each of these torques individually. So torque 1, let's call this object 1 for force 1 over here. Not object 1, just force 1. So this will be 4 meters times 20 newtons times the sine of 90. And that's just going to give me 80 newton meters. Because sine of 90 is 1, right? So it's just 4 times 20. Now, as a result, since this object causes it to rotate counterclockwise, again, look at this force. This object rotates counterclockwise. We've called counterclockwise positive. So that answer is definitely positive. So the other force produces what kind of a torque then? A negative torque. The second one, the second force is 3 meters away with a force of 15 newtons at an angle of 30 degrees. It's going to give me 22.5 Newton meters. Well, I need to tack on a negative to this answer because it will cause a clockwise rotation by itself. By itself. Okay, and that's what I want to emphasize here. That's the key that I think a lot of students struggle with. Jot that down when you're ready to look up, please. Imagine this here, right? This is the rod itself. Okay, right there in the middle. Here's the pivot point. What you need to think about for these problems, for the signs, okay, is what if I just push down alone this way? That's what we've been talking about the whole time. If F1 was the only thing to act, it would cause it to rotate counterclockwise. Agreed? If F2 was the only thing to act, even though it's at an angle, still do it. Which way does it rotate? Clockwise in that case. So F2 causes a clockwise rotation, and therefore the torque produced by F2 has to be negative. This negative sign does not come from the arrows because they're down or stuff like that. Nothing to do with the force direction. It has to do with which way would the object rotate if only that force were acting on it. That's how you come up with the sign. Okay, so again, to jot this down, this would cause a counterclockwise rotation. This would cause a clockwise rotation. So one is positive and one is negative. Before you move to get a quick leg break, the net torque would be the sum of these. So as a result, because this is the net torque on the object and it's negative, we know that it will move clockwise. So the next few examples is what I went over in the class. So just take a look at that. either the class video or mine. Mine video doesn't have that class exam. You might have looked at the class. Okay? So again, the negative answer simply tells me that it's going to move in the clockwise direction. Okay, the clockwise direction. Take a quick break. Take a break. Stretch your legs and stuff. So I want you to just practice. Go through the process of finding all these three torques, sum them up, set it equal to 0. Remember, guys, yeah, that's a good question. It's a common mistake right away. This is the point of rotation. So everything is measured with respect to this for R. All of your R values are that far away. And then torque counterclockwise to second. Yep. So here's a. Just hold that, right? You would push on this side, which was good. So that's it here. On this side, same thing on the side. So always hold fixed on option. Use your pen as a model for this object. If you need to figure out which way it's rotating, hold your pen where the hole is or where it's drilled in. Distance from the rotational front. The R for F2 would be 6. Remember, your dimensions on here are not the answers you're going to use for R. You're not going to use 4, I'll tell you that. 4 will not show up as one of your R's. If you're using 4, you made a mistake. But this torque is not equal to 0 alone. The whole sum of all three is equal to 0. When you add these three together, right? So you're getting numbers for these, right? When you add these things and this together, you're going to set that whole thing equal to 0 and then some. Because if I don't want something to rotate, I want the torques to be balanced, right? So if something produces a positive torque, and this is negative, and this is positive, hopefully the two positives counteract the negative and give me a 0. So just find these numbers without any sort of like solving at all, and then just add them together and set it equal to 0. What those numbers are? That's unknown. So you call that, so what is force? 10, right? Times the sine of 45 times R. 10 times sine of 45 is 7.07. So 7.07 R goes into T3. And then you're going to solve for R. Okay? Yeah, guys, that's a great point. Again, R is your unknown here. You don't know what R is for F3. That's the unknown. So when you sum everything together, you're going to have R in there, and you have to solve for R. Negatives and positives. So I'm not seeing a lot of negatives and positives. Which of these torques are negative, which is positive? What do you got, Marilyn?
The one furthest left is negative. The one furthest right is negative. The one going straight down is positive.
Yeah, take a look. F1, if you're not sure about your signs, ready? This causes clockwise rotation from this alone. It would go clockwise. This one alone would also cause clockwise. So clockwise is negative, so we have negative and negative there. And the other is positive. If you're not sure, everybody please do this. Take your finger and hold this still. And simply push down. That would be clockwise. Over here, take this one, push up. Clockwise. This one here, push down. Counterclockwise. You see what I'm saying? So physically do it with your pencil. You could always check which way something would rotate by simply holding it still at that fixed point and then pushing on either side. Now you're going to get numbers here. I should do RF sine theta, right? That's what I've been doing. Doesn't matter. FR, RF. Check this number, please. This should be 10 meters. F1 is out here. The rotational axis is here. 6 plus 4 gives you 10. Okay, be careful. That's the one mistake I could see for that calculation. For the second one, it's 6 meters away. Do I have to put anything about sine for the second one? What's the sine of 90 degrees? It's 1, so I don't really need to put that there. Everybody see what I'm saying? Okay, I could write sine of 90 here, but it's not really necessary because this just goes to 1. And then finally, the last part, we don't know the distance. We'll call that r. We know the value is 10 newtons, and we know that the angle is 45. Tau net equals 0. Net means add them up. So let's go ahead and add them all together. I don't have my numbers in front of me. What do we got? Yeah, tau 1, what do you have?
I have 4, negative 15 times sine 60, I got negative 129.9, or
I got the second one already. Give me the third one.
for 25 times 6 is 150.
Got it.
For r, 10 sine 45, I got negative 7.07 r.
Good, and that's a negative. Whoops, I should put negative there, right? Are you kidding me? I hate this app sometimes. I like it because you can present, but you can't erase things well. There's a negative right there. And there's an R there. The key is to recognize that you don't know the lever arm for the third force. That's why there's an R here, because this turns out to be 7.07 R. So where are these numbers coming from in case people are lost right now? This first one is the negative 129.9. Dang it. Why can't I erase anymore? Why is this not allowing me to? The second one is where the 150 came from. And the third one is 7.07 times R. So I literally, negative 7.07 times R. I literally take those three values, sum them together, set that sum equal to 0 because this is a problem that's asking when it is in rotational equilibrium. What is R? Not, is it in rotational equilibrium? Does it rotate? Does it turn? If that's the case, you would simply have a number for R already and figure out these three numbers, add them up. If you get a positive number, it's counterclockwise. If you add them up, to get a negative number, it's clockwise. That was the question we did in the previous one. Now we're trying to investigate if it's in equilibrium, it's not rotating, set equal to 0, what should the value of R be? What do we get for R? Question? 2.84? Yes, agreed? I saw 3 nods, so I'm down with that. That works. 2.84. Is the diagram drawn to scale? Who knows? Let's take a look. No. Right? Would that make sense? For R to be 2.84 based on the diagram? Probably not. So it's not drawn to scale. So where should that force be? It should probably be like right around here where the R is itself, right? A little bit further in. If this were drawn, it's purposely not drawn to scale, right? So you don't know the answer. But if it were drawn to scale, it'd be like right here. That's where that force would really be. Because this is about 3. It's about half of what that 6 was on the other side. That's what I need you to understand for the idea of torque. Is that clear? How rotations work? Positive, negative, counterclockwise, regular clockwise. Now there's a follow-up to this question that it really, I think it confused the other class a lot. So don't fret about this if you're having trouble with this next part. But I did have a follow-up question. Remember I talked about how sometimes I do those follow-ups where like links an old material. So like when we did energy, sometimes I'd say, okay, but now figure out using kinematics, how far would that have traveled? And you got to use your old school formulas with energy. I don't usually put those together in the test, and I'm not going to here, but I want you to also see what's happening. So we answered the first part, right? What should the distance be, r, for it to be a rotational equilibrium? The second part, though, says, is the rod in a state of force equilibrium? Is it in a state of force equilibrium? How do I figure that out? If something was in force equilibrium, what would the sum of the forces equal? What is it? 0. But I have how many directions when I look at forces? I have x and I have y. Right? X can go up and down, y can go up and x can go left and right, y goes up and down. I have z also, but we've talked about x and y. So what I have to consider is this, and just watch for a little bit. You don't have to even write this down. Just watch what I'm doing. This force, right, caused a counterclockwise rotation, but that was with rotations. Now I'm trying to figure out: is it in force equilibrium? Which way does this force act? Give me a word to describe the answer. Which way? Down. Agreed? So I might say in the negative y direction. Is that reasonable to say? How about this force? Negative down for the y, and what else? And negative for the x. So it's down and left. Negative y, negative x. The last force, up to the right, positive y, positive x. So if I want to see if this is in force equilibrium, I got to use my components, sines and cosines. So in the x direction, I'll do it in blue. I've got the 15 Newton force times the cosine of 60. Remember, x is cosine, y is sine. This is back to forces. This is chapter 5 with forces. So this 15 Newton force times the cosine of 60 tells you how much is pushing the x. So to see how much is pushing in the y direction, instead of cosine, what do I use? What do I use? Sine instead of cosine. I'm like prompting you with that, right? So I should pretty much hear everyone say sine there, even if you didn't know it any better. So that would be a sine of 60 for the y direction. And since they both push positive, because the force pushes up and to the right, they're both positive there. This is very much like what we did with vectors. Remember with vectors, a person walks across Central Park, then walks at an angle 50 degrees, 2 miles, then walks south. We broke everything up into vectors, found the overall vector. This is pretty much that, but just the easy part. Just find the x's and find the y's. So that gets rid of this first force. Let's put a check next to it. We got rid of this first one. This is done. How about F2? Where would I account for F2? Where would I account for F2? Just in the y direction. In which way, up or down? So I'd put, negative 25 right there. Do I have to put sine and cosine? No, because it's only acting in the y direction. The 25 Newton force is only pushing down. So I don't need to indicate sine or cosine, even though I'm looking at the y direction, because it's only pushing down. So we got rid of the first two forces, F1 and F2. Those are done. How about F3? F3 acts which way? Tell me, please. Which way does F3 act? The force, not the rotation, the force alone. Which way does F3 act? Down and to the left. Be confident, to the left. Down and to the left. Down in the y direction means? Left in the x direction also means negative. So both of these components become negative. So then I have a minus 10 sine 45 for the y, and for the x, minus 10 cos 45. So all you need to do is look at the x direction in blue and get a number for that. If it's 0, it's in a state of equilibrium in the x. Go to the y direction, add up those three numbers. If it's 0, it's in a state of equilibrium in the y direction. Just like the rotation, when the torques add up to 0, we were in rotational equilibrium. If the forces add up to 0 in each direction separately, you have equilibrium in each direction separately. Let's see what happens. What happens when you add together in the x direction? What do you end up getting? About 0.4, you're saying? Around 0.4 Newton. So it's close to being in equilibrium, right? There's a little bit too much force acting this way. Positive 0.4 Newtons extra this way. What about the y direction? What do you get as an answer in the y direction? Negative 19, all right, for this case, negative 19.2. That's a very far answer from 0. So really what's happening here is this object overall is kind of in equilibrium in the x or close to it, but in the y direction it's not. It's not at all, because that answer is not even close to 0. So it's not in a state of force equilibrium because the sum of the forces in each direction did not independently equal 0 each. That's kind of redundancy, right? Independently each. So each of them have to equal 0 for it to be in an overall state of force equilibrium. And because of that. Now again, what you're seeing in blue and red is an extension of this topic. We're going back to forces to do that. What I really need you guys to get your head wrapped around is all this stuff right here. What we did in the beginning of this lesson, of this problem. Is that clear? The rotational part. This kind of stuff is good to know and understand, and I can see that being like a final exam problem. I'm telling you now, this is usually a final exam problem where it's a rotational part, and then afterward I ask about forces because the final is on the whole year. So if I want to quiz you or ask you about forces, maybe I ask you this problem and embed it into the problem. Okay, but as far as your test is concerned, your next test and homeworks and stuff, what you're really being focused and quizzed and asked about is really just this portion of the problem right here. Okay, all the rotational stuff. But again, this is useful to understand force equilibrium. Questions on that? How about this next one? Spend, I don't know, a minute. Spend a minute trying to figure this one out. If you want to talk to the person next to you, you can about it. Because honestly, this is not an easy problem. It looks like it's easy at first, but it's not necessarily easy at all. Okay, but try to maybe consider what's happening in this problem. Read through it on your own. Talk to the person next to you for a second. Again, not an easy question, so don't jump to conclusions. Try and think about what you have to do to calculate the torque. Videos in class. Started it.
Okay. Thank you.
Yep. Let me pose a question to give you a little head start of where you're going here. What did you use for R is the question, right? What is R in this case? Matt, what did you use? 0.5. 0.5? Did everybody use 0.5? Is that, oh, they had their hands went down. Okay, we have 1 as a length of the square. Root 2. Root 2 over 2. So there's several ways to interpret this one. And let me explain, because the root 2 and root 2 over 2 part is actually right, but the 0.5 that Matt said is also kind of right, actually. So let's discuss this. This is why it's a little bit weird. Where is the point of contact? It's right here. Where is the rotational point? It's right here. So it is tempting, and it works if you do it this way, to make this your R value. But the problem at that point then becomes, what is this angle? You see what I'm saying? And you could calculate it. It turns out to be 135 degrees. You could probably even see it if you look at it carefully. Okay, because this is 90, and this is going to be 45 because it cuts this in half. But the problem with that would be you have to then calculate this length R, which turns out to be, it's going to be 0.5 squared plus 0.5 squared equals R squared, and then come up with R. And you can do it that way, and that works. It does. So what you guys were getting at with the root 2, that does work. But there's an easier way to do it. The way I think about this, and it's a little bit tricky to see, so let me show you a little example. If you extend the force vector, you extend it to here, okay? If I extend the force vector and put it at that location, I can use the full 8, and I can now use a 90-degree angle. It's going to have the exact same effect as if you had figured out this distance and then that weird-looking angle right there. By extending the force, and this is something I learned in my sophomore year of college, in mechanics of solids. I forget what the term of it is called, but you can take a force and you can displace it further on, and it's mechanically the same thing. Because if you think about it, the 8 Newton force and the force I just drew in red, they would both cause it to turn counterclockwise, right? It would have the same overall effect, actually. So the idea here is that instead of using this as your R value, right, instead of using that, use this as your R value and apply the force right on that location, and now you have a 90-degree angle. There's a theory as to why you can move the force over, but it's not something I can explain very simply without an engineering background. So for now, you kind of have to just take me on that word that you can actually take this force and continue the vector along the direction until it meets the lever arm at a right angle. This is what I was talking about earlier with the lever arm, with those pictures 1, 2, 3, 4. That's kind of what that was going over there. So with the 4 Newton force, I could do the same thing. I could apply the 4 Newton force right here instead. And in both of these cases now, I'll zoom in so you can see this a little bit better. In both of these cases, the length of the lever arm is simply 0.5. How do I know that? Because this was given as 1. That was given as 1 meter. So 0.5. So instead of using the point of contact, continue to extend the force onto the body of the object, because this is now a 3-dimensional, or in this case 2-dimensional, but it is not just a rod anymore. This is a 2-dimensional object. Extend that force until it meets with the actual rotational axis at a 90-degree angle. So if I put the force here, take a look, this would not be 90 degrees anymore, right? If I put the force there, if I put the force there, it still wouldn't be 90 degrees. But when I put the force directly above the rotating axis, it's now 90 degrees. And it's one of those things, just for now, to take me on the truth of this matter, not to go into the detail. So mathematically now, it just becomes a lot easier. If your angle is now 90, and you got 2 forces acting, both with the same lever arm of 0.5, both at an angle of 90, but they're counteracting one another. The 4 Newton one, right, produces a clockwise rotation. So let's go ahead and write down tau 1. That's going to be 0.5 times 4 newtons. And because it's clockwise, I put a negative on there. And then tau 2 is going to be 0.5 times the 8 Newton force, and that's positive. So I've got negative 2 Newton meters, and I've got positive 4 Newton meters. Question says, find the net torque acting on the object. So I simply sum those together. If you did this problem by using, this is where you can prove it to yourself if you don't believe me. If you did this problem by using 8 Newton force at a distance of, does that turn out to be root 2? Is that right? Or is it root 2 over 2?
Yeah, root 2 over 2.
Root 2 over 2. If you use a distance of root 2 over 2 at an angle of 135, you will get the same answer we got here. Okay, you'll get the exact same answer for the net torque. The other side, it would be the same thing. Okay, again, root 2 over 2 and 135 would be the angle there. It's because the sine of 135 is itself root 2 over 2. Yeah. So you end up getting a cancellation there. You end up getting, it should be root 2 over 2. It should be just root 2, I think, actually. The distance should just be, right? Let's see what that is. If we looked at it this way, right, like that, it's going to be 1/4. If I square them, plus 1/4 squared, it's going to give me 2/4, which is a half, so it's radical 1/2. Oh, which when you rationalize becomes root 2 over 2. Okay. So yeah, if you did it the other way by using this as your lever arm in 135, you'll still get the same answer in the end for this problem. All right. Let's go to the last one. So be careful. In this diagram, let me quickly zoom in to point something out. So R is a dimension. It's not a force. R is the radius, okay? That's what was misleading. The other class thought R was another force that was added on. So R is just the measurement of the radius. So the inner circle has a radius of R. The outer wheel has a radius of 2R. Mike, weren't you talking about something like this the other day with crankshafts and rotating things? The clutch? Isn't this kind of how it works with the different diameters for each clutch? Each gear has a different diameter, right?
I don't know, it's just the one gear, but it's the centrifugal force.
Causes the clutch to move.
Yeah, and then latch onto the outside.
And what's happening is, as you change gears in a car, you're producing either more torque or more velocity. If you want torque, less velocity you get. If you want velocity, you get less torque in the end. So in the end, what happens is when you change gears, it's actually engaging a different crankshaft that has a different rotating diameter. So there's like teeth on the outside of here that it grabs onto. That's why how many of you have driven a stick shift before? Honestly, a stick shift. Have you ever heard like clashing of the gears if you do it wrong? That's physically what's happening. It's running against it and they're grinding. So when you shift between one gear to the other, it should be nice and seamless. If you start using a car and you constantly are grinding the gears, you actually ruin your gear train. So what's happening here is that this object is rotating. These forces are applied. All these forces are at different distances. And the question presented is, do these forces cause the wheel to rotate? They are acting and exerted tangentially to the wheel. We need to know what that word means. Tangentially. Geometry. Tangent. Tangentially. Tangent. Come on, somebody else. Yeah, sorry. What does tangentially mean? Matt, go ahead.
I know how to draw it. I don't actually.
Across the circle at the.
That's a secant.
It touches one foot.
A secant goes across a circle.
Oh, I mean like on the point on the circle.
Good. It's hard to describe, but yeah, you're right. So it's a line that coincides with the outer perimeter of a circle once, right? It coincides with the circle only once. It touches only once. Okay, these are all tangent lines, all of them that are drawn here. The forces are all tangents. The radius is obviously drawn radially. So the question is, do these forces cause the wheel to rotate? So before we answer that question, answer this question. If something were to rotate, or were not to rotate, what's the difference in the sum or the answer? When it doesn't rotate versus when it rotates, how does that change your answer to answer this real question? What are we looking for here? If it wasn't to rotate, what would the sum of the torques be equal to? If it was not to rotate at all, if it was in a state of rotational equilibrium, what would the torques add up to? What would it be? 0. That same number, it keeps going up to 0. When you hear equilibrium, think 0. Please think either the torques add up to 0, or if it's force equilibrium, the forces add up to 0. So in this case, if we get the torque from each of these and add them up, and we get 0, it's not rotating. If we don't get 0, it's rotating. Okay, similar to one of the examples we did a little while ago, but now a little bit different of a diagram. So, before we begin this one, we have to look at these forces and really identify which way they're causing it to rotate. This force, right here, causes what kind of a rotation? Clockwise or counterclockwise? Everybody. Counterclockwise. I hope you all said, because already follow the direction. It can literally only loop that way. What about these three? They're all clockwise, and that's be careful because these two are obvious, right? Everybody sees that. This one also causes clockwise rotation. So since these are clockwise rotations, these are all going to be negative torques. This is a counterclockwise rotation, so that's going to be your positive torque. Well, I don't have any numbers. Who cares? You don't need numbers. Use variables. R, 2R, F. So let's take a look and first isolate this one here. So if I look at this first force that's causing a positive torque, how far away is the force from the rotating axis. How far? Not 3r. This whole length here is 2r. Sorry, the whole length, because the 2r looks like it's that dimension, right? Yeah, I can see that. So this is r right here. This is another r, so a total of 2r. This 2r is really not written well, by the way. This should be written like right here to show that the entire length from center to outer is 2r. So we know that this force is acting, again, this force here is acting at a distance from the fulcrum or the rotating point, in this case the rotating point, a distance of 2r with a force of F. So the torque provided from that first one is going to be 2r times F. Sine of what angle? What are the angles here? When something is tangent to the circle, what's the angle? What's the angle between, ready? Take a look. Take a look, please. Here's my lever arm. Thank you. And here's my force. The angle is 90. This is a theory you learned in geometry lecture, and you probably wondered, how the heck am I learning this theory? Any tangent line is always perpendicular to the radius. That you actually learned last year. It's one of your theories. Any tangent line to a circle is always perpendicular to the radius. It's always true. So for all of these cases, we have perpendicularity. This one is kind of drawn a little odd, but it is perpendicular. Okay? This next one here, perpendicular. This next one out here, perpendicular. They're always going to be 90-degree angles when it's tangent to a circle. Okay? So that first one was a positive torque. The next three, right? The next three are all going to be negative torques. So let's start with this one up top here, please. So this force right here, how far away is it from the center? 2r. This distance right here is 2r. So I know that this value is going to be 2r times however much the force is applied, which is F. So already, before I go any further, equilibrium, yes or no?
Yes.
If it was only tau 1 and tau 2, it's equilibrium. Sorry. But for the whole thing, I mean, for the whole thing, what can you conclude? These two are in equilibrium for sure. Right? These are balanced. You see this? 2RF, negative 2RF, those are balanced. But what are these going to cause? These are going to cause an extra torque that's not being balanced in the clockwise direction. So the overall scenario is not in equilibrium for sure because I've got tau 3 and 4 that are causing me a bit of a problem. So tau 3, let's use this force out here. Okay? This is a force F at a distance, again, 2r. So it's, again, the same thing. And then the last force right here. This is the not tough one, but this is different. This force is 2F. It's double the force of the others, but what's the radius? What's the lever arm only?
1R.
Yeah, it's simply 1r. This distance is 1r, but the force is 2F. So you have 1r times 2F. So it turns out that all of these are producing the same amount of torque. All four of these forces produce the same torque. It's just that they're different orientations. Some are positive, some are negative. One of these is R and 2F versus 2R and F. But it's the same thing because multiplication is commutative. Right? If I do 2R versus F multiplied by F, and then 1R times 2F, these are literally the same things. So if I want to find out the total torque, I add them all up. Okay, I sum them together. Why am I putting negatives for all of these? Because they're all 3 negative. So the 2RF minus 2RF, the first two really cancel technically, if you think about it that way. These kind of balance each other out. And what's left over are these other two forces, which is negative 4RF. Okay? The answer for this is that it's moving in the clockwise direction because the overall torque is negative. Remember, clockwise was negative, counterclockwise was positive. So the overall motion is going to be, in this case, again, clockwise. What is the answer, though? We don't know. The answer is a function of what? Our answer, look at our answer. It's a function of two things, R and F. So if I had a wheel, I could choose any R value. If I want the overall torque to be, I don't know, 37 Newton meters, I could know what the force acting is for each of these and pick an R value that works and design it based on that. So in engineering, you usually know the end goal, and then you come up with the parameters involved in it. So if I know how much torque I need on this, and I know what the forces are, I can design the geometry so that R is a specific value, right? Or I could go and say, you know what, I know the R is the same value. How much force should I apply? What should F be? If I know the overall torque, I can solve for F. Okay, or maybe I tell you R is 7, F is 12, find the overall torque now. All you gotta do is plug in 12 and 7, or 7 and 12. Okay? There's a question in the homework I want to go over real quick, a diagram of, and I only bring it up because Ernest asked about it. It was a good question. It was number 56. Okay, take a look at your homework here. So this homework is due tomorrow. Number 56 refers to a diagram earlier in the book. The problem says something like, refer to diagram, blah, blah, blah. It's on page 290. So jot that down, please, so later you're not lost. Because the question is on page 296, but the diagram is on page 290. The diagram is on page 290. The diagram shows a woman holding one end of a plank, a man holding the other end of a plank. The woman applies a force up, F1. The man applies a force up, F2. The man and woman have a child. The child sits right here, and the child sits with a weight, mg. Remember, the weight of an object is mass times gravity. The dimensions in the diagram are given as 3/4 L and 1/4 L. This is the scenario that's given. The point of rotation, I should erase the right end, sorry. The point of rotation is on the left side. Only the left side, okay? The point of rotation is on the left side. So think about what we talked about in class today. If I put a force where it's going to rotate, so this is fixed, right? I can push here and it rotates. If I push here, is it going to rotate? So does this force have any effect on the torque? Because R is what? What is R in this case? Zero. In this case, what is the R from this force? 3/4 L. What is the R from this force? 3/4 L plus 1/4 L, or just L. 3/4 and 1/4 is a full length L. So this force does not have to be taken into account. Now, the tricky part of this problem, besides the diagram, was it said, what is the kid's weight? Find out the child's weight. That was the question. But it didn't say, assume it's not rotating. So you have to assume that this object is not rotating, and therefore rotational equilibrium exists, so that the sum of the torque from this one and the torque from this one summed together equals 0. Okay? So the idea here is that this produces torque, this is your force. Remember Fg, here's your force Fg. Your goal is to find, if you don't want to write mg, the book uses mg there. But if you don't want to actually write mg in that location, you could just write Fg. F2 is given, it's some number. F1 is given as some number in the problem. Your goal is to find Fg. It looks like you can't do it because L is unknown. But when something's unknown and you don't need it, what happens to it usually? Just like mass, it cancels out. Okay? So use this as a little bit of a hint for number 56 later on. All right.